Well, I'm happy to introduce Daniela Mitterberger. We have a break until we figure out some technicalities for her presentation, but she's ready, and we're really excited. She's a PhD researcher at ETH Zurich, and she's the founder and director of MAEID, Future Retrospective Narrative. So welcome, Daniela. We're really excited. So the floor is yours.
Thank you very much. Also, thanks for the invitation. I'm very excited to show you my work. I know it's late in the day, so I try to keep it short, which is always a wrong promise. So I called my talk "Workmanship of Synthesis: Digital Devices, Synthesizers, and the Human Body." You will see throughout my presentation, I'm obsessed with the human body. I'm also obsessed with machines, mostly robots, and performative architecture. And in my work, I investigate different human augmentation principles and workflows, especially for computational design and robotic fabrication. So a lot of the work that I'm doing is actually trying to build things with human augmentation, design it, but also fabricate it. Of course, human augmentation in computation is a topic that is discussed since a long time. It was initiated to the common public with a big bang by Doug Engelbart with the presentation that was later called the mother of all demos. Of course, everyone knows that one, but I'm still very fascinated by the ideas and the futuristic concepts that they developed and that we're still catching up to. So the presentation of the mother of all demos was on December 9th, 1968. And Doug Engelbart changed the tech industry profoundly by introducing NLS system, which includes many important inventions, such as computer mouse, online software, including window-like interfaces, and also things that we now call hyperlinks. Also, which is very funny, if you read his texts, he's writing a lot about architecture and envisions actually the graphical user interface that we're all now using, including the perspective view, top view, section view.
I can copy a word, a word might copy after itself.
System.
In fact, that pair of words I like to copy after itself, and I can just do this a few times.
You can see the mother of all demos, how it was presented.
Other entities like
beautiful how it was presented via the projection over the face of Doug.
Great. So I could get myself some material on my blank piece of paper, and then I'd say, well, this is going to be more important than it looks. So I'd like to set up a file. So I tell the machine, all right, output to a file. And it says, well, I need a name. I'll give it a name. I'll say it's sample file. And I'll say, please output it. It says it did. And then it comes back automatically with an origin statement or header. Tells me the name of the file and the date and the time and who established it.
Okay, just leave it like this. Okay, MLS is short for online system, and it lets you work and communicate with others in countless ways. So you can edit, you can draw images, you can manipulate and organize files, send messages, and even do video conferences, what they showed actually with the mother of all demos. And the whole idea was to augment the human intellect through collaboration. And I'm very interested in this part of collaboration. And he said that in the 1962 proposal, where he wrote up the proposal of the project first, said he's working on a way of life in an integrated domain where hunches, cut and dry, intangibles, and the human feel for situation usefully coexists with powerful concepts, streamlined terminology and notation, sophisticated methods, and high-powered electronic aids. A contemporary of Doug Engelbart, Ivan Sutherland, that of course everyone knows, developed in 1968 the first virtual reality and augmented reality head-mounted display systems, and as well the graphical user interfaces to allow users to interface with the machine. So researchers such as Doug Engelbart and Ivan Sutherland enabled the development of different software to create, display, and edit computer-aided design that have allowed designers to communicate their ideas via screen-based interfaces. Why I'm showing these things is because we are not much further. And that's where I'm hinting to, and that's also where I'm working on currently. So this was 1962 and 1968, where we started to work on graphical user interfaces. So current user interfaces in architecture and engineering and construction still focus mostly on graphical user interfaces and do not offer any digital embodied workflows. Furthermore, the current technologies regarding direct and interactive manipulation of design and fabrication outcomes via bidirectional communication workflow is still in their infancy. So mostly we are still working exactly how they envisioned us to work in 1960. Other disciplines, such as medical robotics, are way further than us in architecture. So they already try to integrate and actually introduce human-machine collaboration workflows directly in the work process. On the right, you can see a classical fabrication workflow in architecture and engineering and construction, where you see it focused more towards the full automation system, which excludes all aesthetical and technological potentials that human-machine collaboration could bring. So these are all the things that focus and push me to focus on human augmentation principles and workflows for computational design and robotic fabrication, because I deeply believe that they bring not just technical advantages, but also aesthetical and philosophical advantages with it. Of course, the first question, if we want to work on human-machine augmentation, is how we can make a human communicate and collaborate with a machine. And communication is a big part in the work that I'm doing. And how to communicate is, there are different ways in how we can communicate. It's how we can sense. I'm especially interested in how we can use the human body as an interface, using different kind of sensor inputs such as EEGs. I mostly work on eye tracking a lot and augmented reality. Also work a lot with verbal commands and gestures, because they're very closely linked to what we understand as intuitive communication with something else. So I'm very interested in non-verbal communication besides voice inputs, because these allow us to actually reach different levels of interactions with machines. And of course, it's not just about human augmentation, it's also about extending the machine, which means what can happen if we extend the machine with human capabilities that the machine inherently does not have. So besides the technological advantages that are, of course, that we can save time, we can work with environments that are complex, such as construction sites. I'm also very interested in what it means for the design realm if we bridge human and machines. And I'm especially interested in two terms, which is first chronotopic architecture, and a second one, the workmanship of synthesis, which are for me very distinct new features that are unlocked when we are working with human-machine collaboration. Chronotopic architecture. What is chronotopic architecture? The term chronotope is derived from two Greek words, chronos, time, and topos, space. In literature theory, the term exists. It means and describes how different combinations of time and space are represented in language and discourse. For me, chronotope and chronotopic applied to design specifies the influence that a unique place and time can have on architecture and its domains of relations and vice versa. Chronotope therefore reinforces the idea of architecture as an indissociable network and a unit of interactions. It challenges the idea of architecture as a discrete and isolated object tuned to maximum efficiency, and it makes space for an aesthetic of interconnectedness, imperfection, and unpredictability. So the concept of chronotopic architecture is closely related to the term event in physics and relativity theory, borrowed from French. What is it? An event is the instantaneous physical state or occurrence associated with a definite location and time, defined by a point in space-time. This is, for instance, when a cup shatters on the floor, it's very closely linked with time and the location where the cup is shattered. While the term chronotope only contains time and space in its direct translation, it also refers to all actors present during an event. So the framework of a chronotopic event can therefore be described in terms of space, time, and actor. Space is defined by 3 spatial coordinates. Time can be described by 1 coordinate, t, to specify the moment in which the event occurs, and the actor can be described by 1 coordinate. So these 5 coordinates form for me a 5-vector description associated with a chronotopic event. So 2 chronotopic events can either happen at the same time, but in different spaces, or at different times in same locations. So therefore, 2 separate chronotopic events will never be identical, as either time, space, or actors must change. Architecture in such a context becomes hyperlocal and hypertemporal, making every chronotopic event and architecture unique. So for me, this concept contrasts very strongly with normative definitions of architecture that define space as an objective form or associate architecture with discrete qualities defined by clearly identifiable and individuated objects. These are a bit of the thoughts behind the test. These thoughts in an AA summer school in Melbourne, where we link the design and the creation of a digital model with the user creating it at the same time. So we used sensors placed on the design itself that changed the design of the architecture in real time continuously. So there was no frozen moment of this architecture. It was only able to experience it on the screen or in virtual reality, but there was no final state of this architecture. The test was, or the tryout was, what happens if we link the one who creates or designs the architecture that closely with the geometry. So these thoughts of chronotopic architecture are not just linked for me to purely digital form or digital architecture, but for me it can also, or it also has to be specially translated into the fabrication of architecture, and especially in the production of architecture. So these thoughts were there when we started to work on the Magic Queen that you see here, that was exhibited in Venice Biennale last year, where the idea was to produce an architecture that will only be existing in that form and shape for that specific location, produced during that specific time by these specific people. For that we used cell 3D printing. I'm just gonna try to skip to the front so you see a bit how it looks. No, that does not work. We don't skip to the front. Let me try. Well, that was the final look. So the whole idea was the material changed according to the temperature of the room. And to result in this form, we had to do an excavation of the individual modules. And the user that excavated it, or the person, the human that excavated it, actually could decide at one point what to stop. So we had a digital model in the beginning, we reduced with the robot, but a combination of this specific material, which inherently already has an imprecision in itself, and the human, which are unpredictable, resulted in an architecture that not just, we could have never predicted. It was within a specific framework, but we could not reproduce it in the same way. It also changed in the whole period of the exhibition. Chronotopic architecture does not stop with the final architecture. It also continues with the idea of how we inhabit a chronotopic architecture. That means it's linked with the idea that it's not just physical form, but it's also linked with, that's Tiziano, partner at the office, with the idea of we have machines and robots that observe the architecture and create shapes like this one, where you see that's through the camera of the robot, observing and scanning the creation, and at the same time there was a sound environment with it that continuously changed according to what the robot saw.
Robot is
that was the one column on chronotopic architecture. The second one is workmanship on synthesis that I'm very interested in. As you already saw, I like this collaboration with a machine and a human, where you have unpredictable elements that you cannot compute beforehand. So the workmanship of synthesis comes from the idea that reproducibility of a machine is one of the essential advantages, and ultimately increasing efficiency and saving labor time. So that was one of the most important reasons of the second industrial revolution, why we moved to machine production and separated design and fabrication realm, actually. Yet, if we focus only on machine fabrication, it does not offer any surprises nor discoveries on the side of the human. Because once you know one object or one architecture, every other object from the same production line will look exactly the same. To quote Timothy Ingold here, the separation of design from making has resulted in a built environment that has no flow in it. You simply cannot design an improvisation or an adaptation. David Pye wrote in The Nature and the Art of Workmanship about two things. He wrote about the different concepts on crafts and workmanship, and the one was workmanship of risk, and the other one was workmanship of certainty. What does it mean? So workmanship of risk is talking about the idea that the quality of the outcome still depends on the maker's judgment or the designer's judgment and the decisions and the care during the process. And even though maybe machines or devices were used, the client can read multiple layers of information on the piece, similar to a cartography of events that happened during fabrication. So that means the craftsperson might have been tired, might have been inspired or excited or distracted during a short amount of time, and results maybe in an imperfect straight line. It might result in a shake or a collection of patterns. It might be surprisingly beautiful. The workmanship of certainty is which comes from the machines. So that means the quality of the outcome still depends on the predefined design before the production starts. And it has the big advantage, of course, that it can increase productivity. So the question is actually how we can create a third one, which is the workmanship of synthesis, where the quality of the outcome of a design or a fabrication or an architecture still depends on the maker's judgment, but remapped with machine and material constraints. So that means that the human and the user can still make decisions and have care during the process. But at the same time, a machine constraint can enable the user to increase productivity while keeping originality. So to find the balance between certainty and risk, the craftsperson or the user or the designer or the architect can be or should be equipped with tools that regulate human input within specific quality standards. So while still allowing them to apply decisions during manufacturing, the machine kind of outbalances what the human can do. And I really love the idea of a synthesizer. And I think a design process where you use a synthesizer as a filtering tool is something that I'm extremely fascinated by. So the design of the tool and the interface becomes very much part of the art or the architecture. And the focus shifted from the final product to the process of making. So the musician who authors a tool allows at the same time other artists to create unique pieces with it. Here you can see an annotations of Stockhausen. So chronotopic architecture supports such a workmanship of synthesis that reveals a temporal and spatial categories of a fabricated object or space. So such spaces redefine the notion of site-specific design by linking the human presence within a specific time frame and a specific location, and brings, of course, its own complexities, its own problems with it. But I'm very, very fascinated by these things, and I'm very interested in how they can be translated into the design realm. Throughout my PhD, I'm trying to answer these questions. It's an ongoing work. It's difficult to answer. In my experience, it's not you cannot answer it only on a theoretical level. You have to test it and you have to try to actually see and perceive what happens if you expose yourself to such design processes. And I have two key projects that I want to show you a bit more in detail. The first one is augmented bricklaying, which focuses a lot on this idea on chronotopic architecture, where the one who's fabricating is very much closely linked to the machine, and it's only possible in this specific constellation. And the second one is interactive robotic plastering, which works on this idea of workmanship of synthesis and the production of a design aesthetic that only works because of the specific technical setup. Augmented bricklaying is a project that we finished in 2019. it started with a client that came to ETH, to Gramazio Kohler research, and they wanted to have a robotic fabrication building like it was in the Gantenbein winery you can see on the left, where the whole facade was robotically fabricated. And instead of reproducing a robot facade that was already done 12 years ago, the question was which kind of new technologies are out there with it, and do we have at our hand to produce these new kind of facades. We focused on augmented reality. So both projects that I will show focus on augmented reality. This one focuses on human-guided fabrication, and the other one on human-instructed fabrication. And here you see the winery, the final result of it. Similar aesthetics, but completely different technological tools used. And the question was, okay, if we use augmented reality, how can we fabricate complex brick walls with it? And we had, well, there are three different ways that you can fabricate brick walls. Normally, the first one is manual fabrication, which depends very strongly on templates and guiding systems. It's very expensive, it's very difficult, it's very exhausting. Then you have robotic fabrication, which is great. You can directly fabricate from 3D, but at the same time, you have very strong limitations. That means you cannot, you have on-site limitation use, and then you have also limitations of materials. So you cannot normally use mortar. So all these materials that are not predictable, they're not very good with robots normally, especially not if you try to focus on a purely automated process. The third one is the aim of combining actually augmented fabrication, aims to combine the advantages of the first two, where you say that you have, you keep the advantages of manually assembly, like dexterity, and you keep the advantage of robotic assembly, such as geometric precision. So here you see the final facade, and the idea was to have a design which very strongly shows the use of mortar. Why? Because only with this technology you can use something like mortar. So we wanted to have the mortar almost as high as a brick element. This is another picture of the facade. How does it work? We're using a custom visual inertial object tracking system, which tracked the position of objects in space. We collaborated with Incon for this one. And it can tell you where a brick has to go and where the brick is currently in space. So it's super different to the other augmented reality systems that use only holographic fabrication. That was the first big difference. And the second big difference was, how can you tell a Greek bricklayer what to do if you can only use an interface? And I was working very closely with bricklayers, and I observed how they worked. And I saw that they don't adjust like we do objects in 3D space with a rotation in all dimensions, but actually what they do is if they want to rotate a brick in space, they hit the brick at specific locations. And that's how they reach the final location in 3D. So any kind of rotational all dimensions that we used, that immediately from Rhino, I tried to just show them like this, they didn't understand. So what I was doing, I was implementing this logic that they inherently have into the computational design logic, where they saw the location of where they have to hit the brick, and the strength of the hitting was visualized in the strength of the arrow. And the combination of this placed the brick at one point in the right location. And it was very simple for them. You can almost call it, I mean, similar discussion. I mean, you have gamification elements in that, undoubtedly, of course. But it was working very well. So the bricklayers saw where to place where to hit the brick. It's like, you know, these games where you hit the things that come out of the table. And at one point, they will disappear. But also the bricklayer can decide if it's fine. So it's not like that the machine stops you. The human still has the decision to say, it's precise enough for me. I don't care. I want to go on. That's still fine. Machine will register it. You have an imposition for this one, but the user can go on. Further, also the mortar amount. So each mortar was differently. The quality of video, the brick index. So all these kind of interfaces was important for the user to give agency, so that it can actually decide and understand what is happening. This was our system setup. I know, it looks like a stock photo. It's not. So actually, we had to split it in two people. The reason for that was we had to finish the facade in 3 months. And with one person, we didn't know where to place the camera in a good way. Because humans, the system was not stable enough to actually allow the counter compute if you turn your head too much. And if you have the camera here, you were obstructing it with your hands. And you had to move the camera to make the IMU work. So that's the setup. So we had one computer for calculation, one computer for debugging and visualization. All, of course, that you can walk around and move through the construction site because so that was the setup, how it was looking like this, so that you can actually move around because all the walls were 5 by 5 meters and you had to be on the scissor lift, so everything had to be without cables. So we decided, we had tried different kind of AR setups. We tried head-mounted displays, we tried tablets, we tried a lot of things, but in the end, the thing that worked the best for this specific case study was screen-based. So we actually moved the screen along with the humans to see what they have to do. So this is the setup, how they were working. Just want to show you a quick video. So yeah, so that was the site. It was in Katerini, beautiful. It was a winery with the view on the to the sea. This is some of the final shots of the first art. So this is how it worked. So we had one operator and one mason. At the end, some of them, when they got very good with the system, they did both. So here you see actually the abundant amount of mortar that we are using, which if you ever work with a robotic process, you know what kind of nightmare it is to work with these materials. Also, we used handcrafted bricks that were all a little bit imprecise. So all these kind of things are normally not very good to work with any kind of automated system. Yeah, we are, yeah. Got better. So here you can see actually how the interface is working. I met a lot of people talking about is it a good thing or a bad thing that we use gamification in these moments. Maybe for later I can tell you the answer. But so yeah, this is some of the final pictures where you see that the mortar amount is really almost as high as the bricks in themselves. So these are just some pictures of the final facade. I think for me it was very interesting because it was the first, it was an actual building project where you can test a lot of these concepts and you just actually ask what it means to do that and what are the results that you can take from that and what works and what doesn't work in these systems. The second project is IROP, Interactive Robotic Plastering, which is a project that we finished last year, and it started off with this idea of how can we overlap the design realm with the fabrication realm. And it doesn't make a difference if the human designs directly on site, and doesn't make a difference if the human gives design incentives and kind of disrupts the design process with that. I mean, it started with this whole idea where you say that, of course, robotic fabrication, I mean, most of us are ETH here, so you know all these pictures, but robotic fabrication is great. It can do specific things, it cannot do other things. And I think that's something that is very important. I mean, it was very good, it led to specific, you know, it led to significant improvements in production, it opened up new design opportunities. So it's great for specific purposes. And like, it's great if you have well-defined and linear sequences of action, if you have very consistent work environments, if you have very unambiguous materials and very predictable processes. But especially if it comes to materials like we saw before with mortar, or for instance your plaster, it's very difficult to translate that into an automated process. And the difficult for that is manifold. I mean, the difficult for this is, for instance, that the material in itself is very complex. That means it changes according to the different environmental settings. It changes. It's very hard to simulate. It's almost impossible to simulate. So it's something where we have to actually keep the human in the loop. And so we proposed the IROP, which combines the human capabilities with robotic capabilities and digital technologies to support automation. And IROP tries and enables users to engage intuitively with an in situ robotic plastering process. So it actually utilizes the user's hand movements to program intricate robotic spray paths, and by that capitalizing on the embodied knowledge of designers and skilled workers. And the system that I developed allowed users to design complex digital models in minutes and to rapidly generate different and multiple design alternatives and preview them, what they mean in situ, on site. And at the same time, instruct the robot by demonstration. So the setup architecture of IROP consisted of a computational setup, which I call a stylistic filter selection, a user interaction tracking setup with a projection mapping for the interactive design mode, and a robotic fabrication setup for plaster spraying. So we tried different things, but what worked the best for this kind of setups was to actually place the human alongside or next to the robot. And so the 3D design is interactively designed and then fabricated. So the user follows a routine of alternating between interactive design and fabrication sessions. So that was our hardware setup, which consisted of this user interaction tracking setup that you can see on the left side, which had a projection mapping and a motion capturing setup, and the robotic fabrication setup on the right side, which included the UR10 spray gun and pump. And it was a specific workflow, so the design was working differently. So the user first selected filters, so you selected specific styles that you liked. You could also design your own styles. It depended how good you are in programming. So we said we have different users. You have users who can program, who users who don't program. So users who don't program, they could pick specific styles. And then the other ones can create their own styles. It's a bit like, that's why also the word filter, it's kind of, I understand it as a 3D Photoshop thing. So the first thing is you pick your filter, and then the second one is your interactive design mode, where you localize your design and you adjust your design. And then you can decide if you want to continue designing or if you want to finish designing and directly go into fabricating. And then you can decide if you want to continue working or if you want to end the process. So here you can see a run through of the workflow where first the users picked a selected filter setup and then they localized, they designed and they adjusted the design on the fly, and then they fabricated. What was at the core of the interactive computation model is of course the tracking of the user input, but also the remapping of the analog human input into robotic output and the generation of the trajectories for the robotic arm. So for instance, the hand position in space was translated into robot target planes. The hand distance to a target surface was translated to an end effector distance to a target surface. And the gesture velocity was translated into the velocity of the trajectory of the robots. So this is also where most of the design decisions are happening, in how we remap things. So this is an example of this remapping. So for instance, in one of the filters, we used the carving effect. The closer you were with the hand to the surface, you got a rippling effect because the spray nozzle distributed the wet material. So the further you were, the more smooth outcome you had of the design, and the closer you were, the more rippling you got. So here you can see what the user saw. It was both audio visual, so it told you what to do, and at the same time it showed you different steps, so you could go through different modes, and different modes allowed you different things. So here you can see one of the users working, and you also had fabrication parameters visualized. So that's what I said before, it's not just visual, it's also audio. So it's the linking of both things where you can say you have different modes, and in these different modes you can pick different things you can do on the construction
Welcome
site.
to the construction site. Please mark the points on the ground.
That was my good friend.
Points are marked, projection is starting. You can start drawing. Welcome to the construction site.
So to validate that it's not just concepts, and we actually tested it. So we built for 3 weeks a wall in that with that design workflow, design and fabrication workflow. And at the same time, I tested what different designers would do with the computational setup, with this idea of the remapping library that I developed, and what kind of different outcomes could we get in the design realm. So these are some of the filters that the students were creating with the setup, where you either have one-to-one translation for the human input, such as a hand drawing filter, or you have very abstract translations where you say, you just give one input and this creates the whole design. So you can decide by yourself how much do you lean the design towards the human input and how much do you lean the design towards a computational or algorithmic design logic, such as in the agent-based filter. The students like the twinning filter, so that's what we did for the fabrication on site. And here you can see a time lapse of how we fabricated it. So this is a video that just shows some of the results. And what I was very fascinated is what I call micro gestures. So when you were visiting the structure, there were a lot of things where you that were surprising. The idea that I asked the students before, do you want to have one designer or do you all want to design? Because with this kind of setup, the question is also, I mean, it's about authorship again. It's like, how many people do you want to have to design? And they decided that they all want to design with the same filter system. And the interesting thing is that you could see at the end which student did which course. So you really clearly saw that some people were better with that kind of filter than others. So here you can see how you can adjust the design. The different colored circles show the height of the bump in that location. Also, the robotic fabrication setup was adjusting in real time to what was sprayed, because that's why we have a standing interrelations in the front. So you need to adjust what was actually sprayed and what's the actual as-built state in comparison to the desired state with materials such as plaster. So we had to be quite rigorous, because if the design team was taking too long with the design, we were always delayed. We tested different things, also discussion on designs. They tested an online platform to vote for designs. That didn't work out. At the end, they were just individually deciding what they liked. So these are some of the results of IROP. There's some pictures of IROP. And almost done, I promise. This is just why I show this one. This is another project done with the office. Is all these experiments or the tests that I'm doing, they have this kind of aim or this big desire to link this architecture as an interface with actors, human and non-human, and an environment, and also transform architecture to a performative space that is ever-changing, growing, and decaying, and as well as in the inhabiting space, but also in the way how we design or fabricate it. And for me, that's very much linked not just to one medium, but all different mediums that, if I manage to make it play, no, that would be great. No, but not. Okay, then wait. Well, so this one should move. So what you can see here, I'm going to describe it. So what you see here is, so that was another installation in Spain that we did for the Princess of Asturias Awards. And it was what you saw before from the Magic Queen. It was trying to push this further. It's tackling similar questions of this, what kind of architecture could come out of this kind of processes of working and designing and fabricating. And what you could see here is that's actually, there was a camera at the front of the robot that was scanning the grass. And by scanning the grass, it was analyzing what is green and what is not green by deciding if it should water or if it should not water. So there was a kind of a data set that decided where should be specific plants, but at the same time, we used, so the robot was watering, was picking seeds, and was taking care of the structure. And the picking seed, but was not precise. So what we used was an air blowing system to place the seeds, to again make kind of this idea of this imprecision. But what I want to show here is this idea of having video streams, having camera vision system, having robots, having humans interact at the same time to create this kind of, this weird environments where you start to negotiate. And of course, we're not there yet. So all these are experiments on the process, on the way to get there. So each experiment tries to get one step further in this idea of creating it as a building architecture. But I think it's very interesting. I'm very excited about it because I have to say, like, these things only work when you experience them. And I think this is one of the things where I say that the fabrication and production of an idea is super important when it comes to this kind of work, because you can only evaluate it once you experience it, which of course is not that good if you want to make videos and this kind of things of it. But it also shows that there are a lot of things where I have the feeling there are not terms for yet, where we miss and we lack the words, and only experience in itself can make you feel it. So this is a bit the kind of state where I'm at, the struggle of the seduction of the words and the seduction of the experience, I think. Yes, that's it. Thank you.